So welcome back, my dears. So this is a similar case to that we already discussed in the previous section, and the only difference is that here we have two spans, that is AC span and BC span. That we already know how to solve these types of problems to find out the moment, that is mH. Okay, so let's continue the problem with the method of strain energy, that is the beams with a redundant one. Okay, so here we have to find the redundant indeterminacy first. That's equal to number of unknowns minus number of equilibrium equations, and we get it as 1. So we can choose VB as a redundant. So the next step is to apply the equations of equilibrium, and here we get HA equal to 0 and VA plus VB is equal to 320. That means here we have a UDL of intensity 20 kilonewton per meter for the entire span 6 meter, and also a concentrated load of 200 kilonewton from 2 meter from the right support B. Okay, so here we have to find out MH for these two spans. For that, take two section lines from the origin. So for the span BC, we can consider B as the origin, and for the span CA, let's consider C as the origin. Then coming to the limits, for BC it is 0 to 2, and for CA it is 0 to 4. Okay, now we have to take the moment about the section line. So consider a section line at a distant sides from the support B, and we will get the equation for MH as VB into H minus 20 into H into H by 2. That is VB H minus 20 H square by 2. Okay, now consider a section line at a distant sides from the support C, from the point C. Okay, now take the moment, that is VB into 2 plus H, then minus 20 into h plus 2 the whole square by 2 minus 200h, and we will get it as VB into h plus 2 minus 10h square minus 240h minus 40. So this is the equation for MH for the span BC and for CA. Now we have to find out the internal strain energy for the entire beam. Okay, in the previous case we have only one span, so we just find out the UI is equal to integral 0 to L m square by 2 EI into dx. Here we have two spans, therefore two moment will be there, and the limit is 0 to 2 and 0 to 4. So first of all, take the first term, that is integral 0 to 2. What is mh square? That is VB into h minus 10h square the whole square divided by 2 EI into dx plus integral 0 to 4 VB into h plus 2 minus 10h square minus 240h minus 40 the whole square dx divided by 2 EI. So we have to add it for the two spans. Okay, so we get the total UI as this equation. Now what is the Castigliano second theorem or principle of Lee's work says? It says that the partial derivative of strain energy with respect to the redundant is equal to 0. So here we chose VB as the redundant, so we have to take the partial derivative and equate to 0. So first of all, I am taking the partial derivative with respect to VB. So take the partial derivative of this term with respect to VB. That means 2 into VB into h plus 2 minus 10h square minus 240h minus 40 into the term along with VB, that is h plus 2 into dx plus 1 by 2 EI integral 0 to 2 into VB h minus 10h square into h into dx. That's equal to this one. Then after that, integrate this term, and we will get VB is equal to 148.7 kilonewton. That means we have to equate this to 0 as per the principle of Lee's work. Okay, that is VB equal to this one, and from the equation of equilibrium we will get VA is equal to 171.3 kilonewton and MA is equal to 267.8 kilonewton meter. So hope you will understood this problem. It's a simple one. Just we have here is two spans, so we have to find two moment and just add the equations for strain energy. Okay, thank you.